Alec, for the lovely introductory talk. What I'd like to talk to you about today is some of the work we've been doing funded by a NASA Emerging Worlds proposal to look at the atmospheric evolution of Venus, especially in its early period when we expect that it may have lost most of its ocean. And to give you guys some broad context, obviously here's the Earth and here's Venus to scale. And like Alex said, we often think of Venus as Earth's twin. If Earth had a hotter twin, they have very similar reservoirs, for example, of volatile carbon. Most of it on Venus is stored in the atmosphere, whereas on Earth it's stored in things like carbonates in the near surface and a little bit in the atmosphere. Similar amounts of nitrogen, we think, and it has a similar mass and radius. And one of the things that sort of drives us to ask questions about Venus is, as a comparative planetology perspective, how do we go from an object that's beautiful and blue and has liquid oceans to something that's a hellish landscape that you can melt lead on and then it rains acid? This transition is really poorly understood. And it's often seen in the perspective of comparative planetology when we look at something like the habitable zone. And this is a figure of my own design. We can talk about many variations later on. But essentially what you can see here is we have the solar system for some sense of scale. And this is, the x-axis tells you about the amount of starlight on the planet relative to the sunlight on the Earth. So Earth here is at 1. Venus receives about twice as much sunlight as the Earth does, and Mars receives about 40-ish%. And a number of Kepler objects and one radial velocity measurement are on this to give you some sense of the diversity of exoplanets we expect and have found around other stars. And you can see that the way we've defined the conservative habitable zone and the optimistic habitable zone are these yellow and red lines, which are directly related to what we think is the underlying process that has driven Venus's evolution. Here in the yellow line is a moist or runaway greenhouse where the surface temperatures heat up to the point where you evaporate some or all of your surface ocean, and it gets broken apart and you lose it. And this recent Venus limit is a consequence of the most recent evidence we have for Venus's resurfacing, which will come up again in the talk. But this was, it could be, about 500 million or 1 billion years ago. This is often based on some older estimates of when that resurfacing happens. So I'm going to use 1 billion years just as a conservative estimate for that milestone. And so the thing I want to point out is that we know that the Earth is habitable conveniently, otherwise there would be no one here to listen to my talk. But somewhere between here and here, there's either one point or several points or a number of underlying processes that drives you from beautiful and blue to bad things have happened. And so one of the things that we ask about Venus is, how did all the water get out of the atmosphere? Like Alec mentioned, it has a very high D to H ratio, which suggests that it lost a lot of water. It currently has incredibly small amounts of trace water in its atmosphere, but not anything on its surface. And the runaway greenhouse atmosphere takes you from something that may be temperate, either CO2 or N2 dominated, and as that water evaporates, the atmosphere becomes water dominated. If you evaporate one Earth ocean, you get something like 300 bars of water vapor in your atmosphere. It's an incredibly disastrous effect in that sense. And what you can do once you put the water into the atmosphere is you destroy it by photolysis, either in the UV, where you break it into hydroxyl and atomic hydrogen, or if you're looking at the extreme ultraviolet, instead of just breaking apart the water, you can actually shatter it into its component pieces. So you might be left with atomic oxygen and a couple of atomic hydrogens if you're pummeling it with an EUV flux much larger than you see in the modern. And so just to come back to that extreme ultraviolet, at smaller extreme ultraviolet fluxes, for example, less than 10 times the modern solar EUV, at the Earth, we find that atomic hydrogen is a minor component in the literature, and that the majority of the hydrogen is bound up as H2 or H2O. Now, conversely, For higher EUV fluxes, you would expect that most of the atmosphere is actually going to be dominated by atomic hydrogen, again, because you're sort of pummeling this water vapor into its constituent pieces. And that brings us to sort of 3 points we can think about in Venus's timeline where we might expect that the intersection between the runaway greenhouse process, which is a function of the total flux that the planet is receiving, versus the escape processes, which are often driven by this EUV heating, can intersect with one another where there's some overlap. And so here on this lovely diagram I've made for you, this is, for example, the formation of the solar system about 4.5 billion years ago. This is today, and this is a Venusian timeline. We can think about the amount of EUV, the extreme ultraviolet that Venus is receiving as a function of time, and we can think about the amount of sunlight that Venus is receiving with time. Like I mentioned earlier, Venus is receiving about twice the flux in both EUV and integrated flux as compared to the Earth. These are relative to Earth values. And one of the suggestions is that Venus lost its water very early in its history. It accreted, went into a runaway greenhouse as part of that accretion process, and never left. And so that Hamano et al. Result from 2013 would have driven the escape of Venus's water in the first 100 or so million years of its evolution, where the insolation was actually relatively lower. It's about 135%, which is still interior to the runaway greenhouse limit from the classical habitable zone. But the EUV flux is anywhere between 10 to 20 or more times larger than the modern EUV flux. And so you're talking about, again, this regime where you're sort of pummeling the atmosphere, which may be predominantly water vapor, shattering those water vapor molecules so you can drive that escape. And as you move forward in time, you have to go from this EUV flux that's greater than 20 times modern to something like 2 times what the Earth receives. And this insolation actually increases in the opposite direction. So the EUV is tailing off, but the insolation is increasing. And so the insolation drives the runaway greenhouse process, but the EUV drives the escape. And 2 other points we can think about. For example, 1 billion years into Venus's history, the EUV has started to tail off. The insolation has increased by about 20%. This is really that sort of knee I talked about when you get below about 10 times modern solar EUV, where the atmosphere goes from being potentially atomic hydrogen dominated to something like molecular hydrogen dominated, if you are dissociating water vapor in the atmosphere. And that atomic hydrogen can recombine. And as I mentioned before, the last resurfacing was about 1 billion years ago, or about 3.5 billion years into Venus's evolution. That's the last possible time that it may have had water. It likely did not. But if Venus was resurfaced, we would have lost any evidence that it had liquid water before that time. And as you can see, the EUV flux is approximately modern, and the insolation is about 175% of the Earth's insolation, which is still well inside the runaway greenhouse limit. Now, the thing that the atmosphere does is it absorbs and repurposes solar EUV. Air is actually the most absorbed wavelengths in the air are the EUV wavelengths, which run from basically 10 or so nanometers up to about 121 nanometers, which is that Lyman alpha line. A little bit beyond that, 125 nanometers. And across that whole region, most of the atmospheric constituents that we're worried about, for example, CO2 and N2, which are the predominant components of Venus's current atmosphere, absorb very strongly in that region. And as you can see, the fluxes vary across a couple orders of magnitude from a very young sun to something more like the modern sun. Now, the EUV that's driving this process is going to essentially move the Venusian atmosphere from Jean's escape mode, where individual molecules are reaching escape velocity and just ballistically exiting the atmosphere, to a regime where there is flow of the atmosphere. The atmosphere is moving as a fluid, and that's why we call it hydrodynamic escape, to a point where it's no holds barred, everyone out the door escape. You're just scooping large portions of your atmosphere off thermally and driving it away from the surface of your planet. This is much more cataclysmic than you might expect for this regime. This is like you are disintegrating your planet bad news. So I'm going to really focus on this middle one here where you sort of have this nice calm regime of things just flowing away in a mild setting. So like I mentioned before, there's three regimes of thermal escape. The Jeans escape limit, where you have high energy molecules on the tail of the Boltzmann distribution reaching escape velocity and exiting the atmosphere. There's the energy limit, where you assume that all the energy, all the EUV that's poured into the atmosphere is used to drive escape. There's the diffusion limit, where you have some escaping constituent that must move through a heavy background gas, and that limits the amount of material you can supply to the upper atmosphere that can escape. And then lastly, you have something called the radiation recombination limit, which I will not touch on, but that's basically you're limited by essentially the pummeling that you're giving to the atmosphere, and it's photoionization balanced by radiative recombination. And most of the rest of the talk is going to look at these two limits, which are at an interplay in these cases. And as a brief note, one Earth ocean lost in 100 million years is a flux of about 2 × 10 to the 13 molecules per centimeter squared per second. So I'm going to throw up some numbers and some graphs, and that's really sort of the benchmark here for the evolution of the atmosphere. The diffusion limit is a strong function of composition. So if you have heavy constituents as your heavy background gas and you have a light escaping gas, your flux is much higher than if you had, for example, a light background gas and a lighter escaping constituent. I will say that this point here is sort of a bad thing to do on a plot like this. There is no diffusion limit when it's H and H2 dominated. You are just limited by photons at that point. There's no diffusion. The research, the literature on this type of project often gets up to about 10 times modern solar EUV for Earth cases, because we're worried about the evolution of the early Earth in a lot of these circumstances. And you can see that by and large, these cases are all limited by diffusion, except when you roll over here, and that's really when you're reaching that energy limit. You have used as much energy as possible to drive escape, but you cannot get to the point where you are limited by diffusion. So this is an energetic limit, and this is just a physicochemical limit. So the model is solving these coupled equations for several components in the atmosphere. At this point, there's no chemistry, so the two components are basically what I tell them to be, either atomic hydrogen, molecular hydrogen, and then whatever heavy background gas. But the mass continuity, momentum continuity, and the energy equations couple these two components so that they exchange energy and velocity over time. And so if we use this model to explore the parameter space for the Earth, which is always a good place to start since there's a lot of literature on it, we see that the model reproduces fairly well to within a factor of 2 or 3 results from the literature for the Earth. And then we get to the point where we can start to ask, well, what about Venus early in its history? Here, we're talking about fluxes that are on the order of 10 times modern, because remember, this is Earth. So if you park a planet twice as, a little bit closer, you get twice the flux, which is what the case for Venus. If you do that, what you see is that the Venusian atmosphere, early in its history, remember, we're at 20 times solar EUV, so it's going to be atomic hydrogen dominated. And if you assume the background atmosphere is a runaway greenhouse case where it's water vapor and CO2 dominated, you find that it's essentially diffusion limited across a broad range of potential hydrogen concentrations, which covers a lot of the parameter space. You can start in a runaway greenhouse way up here, where your hydrogen is being borne by water vapor, and then as you lose that atmosphere, you still follow that diffusion limit down across this whole parameter space. And this is for Venus in its early history. If, for example, we worry about when Venus transitioned across that the recombination limit, where you're actually looking at the escape of molecular hydrogen from a water vapor CO2 atmosphere, these limits decrease and you actually come off the diffusion limit much sooner. So if you drop below a few tenths of a % water vapor in the atmosphere, for example, it becomes much harder to get the rest of it out in this hydrodynamic flow regime. And then lastly, if you look at it about 1 billion years ago, you get the same sort of behavior where it just touches the diffusion limit at one point, but it's energy limited through much of the higher hydrogen concentrations, and then it's well below the diffusion limit for the rest of that. And so in conclusion, we think that the radiation environment for early Venus would have favored rapid escape of the photolysis products, and the parameter space where Venus's atmosphere would have experienced diffusion limited escape is diminished with time. Composition matters, chemistry matters, and that's why that's a second part of this proposal. And I thank you for your attention. Just to point out, these are all pictures from as of AbGradCon 2012, 2013, 2014, 2015. Is it AbSciCon? Boulder? 20. No, I wasn't at 2016. Is it AbSciCon? I've been doing this too long. Yep.
So the blow-off point, what would that look like on a time scale? Like, how fast does that occur once it reaches that point?
It depends on your model parameters. It tends to, you often see that it's sort of episodic, where you'll heat up the atmosphere and it'll go through sort of a phase where it's pushing off atmosphere, and then it'll cool off because of that adiabatic expansion and collapse a little bit, and then it'll just pulse. But if you're driving that, if you're putting enough energy into it to drive that sort of blow-off regime, it tends to be fairly quick, like millions of years or less. Tessa? Let's wait for it.
Okay, there we go. First off, so all those pictures of AbGradCon, I think I may have taken most of those.
You took all those, and I did not credit you, and I apologize.
Oh no, it's just like, wait, these look familiar. Secondly, so at one point in my earlier academic career, I spent a bit of time focusing on potential habitability of Venus in the upper atmosphere, since it's kind of Earth-like. The idea being, oh hey, well if Venus had a lot of water, maybe it had an ocean, and therefore maybe life got established, which then migrated to the upper atmosphere as the greenhouse effect kicked in. From the sounds of it, I'm guessing that's probably less likely, given how early it sounds like things kind of went downhill.
Yeah, so I personally like the mono et al. Result because it's really clever in how it interprets the evolution of the solar system, and it's from their efforts, it has looked like there's a very sharp divide between their type 1 and type 2 planets. So I think that Venus and anything that's close to Venus is going to go through, essentially, it's going to form, be stuck in this runaway greenhouse, and it's going to lose all of its water very quickly. So.
Hey, Sonny, nice talk. Maybe this is something I didn't understand, but what's like the limit of how much water you could have started with such that you would have lost all of it? Are you saying that it happened so fast that you're not really limited by your initial amount of water?
So so there's a couple things in there, right? So when we talk about the D/H ratio, for example, that gives us a conservative estimate on the amount of water that Venus could have had, but then if escape rates were higher, you could have just dragged off deuterium as well, which would have basically erased your D/H ratio. The amount of water you could lose over Venus's lifetime is essentially, if you look here, if you start with like 10 Earth oceans and you're in this very early regime where you're close to the diffusion limit for that whole parameter space, then you could lose 10 Earth oceans in 1 billion years.
Okay.
So it's prodigious the amount of ocean you could lose.
Thanks.
Hello?
Yep.
Thank you for that talk. I was wondering if you might be able to share your opinion regarding what you may think about tidally locked planets around M and K dwarf stars.
Oh man, that's a whole nother session. That's not just a question.
Oh, sorry.
So like the Luger and Barnes result for basically dehydrating M star planets because of their pre-main sequence lifetime and then tidal locking, you can go into these moist greenhouse states even when you're in the conventional habitable zone because of the dayside cloud cover. I think M-star planets are really hard, and I think they're really cool, and we should look at them definitely, but I don't know that we should go into it thinking that any of them are going to be even potentially habitable. So, yeah.
With that, let's thank him one more time.